Very happy to welcome everybody to this final plenary lecture of the workshop, which is given by Sir Richard Friend. And I think with this audience, there is no need to remind you of the several contributions that Sir Richard made to the area. So we very much look forward to your presentation on the management of spin, singlet, triplet, and doublet excitations in organic semiconductors. Please, the stage is yours.
Thank you, Erin, and thank you, Björken, and your organizers. It's been a fantastic conference. I feel really privileged to be part of it. I'm giving the last talk, so I'll possibly be a little bit further away from the core of the meeting than I might have been. But I want to concentrate perhaps less on transport and more on the Coulomb interaction. And I'm going to take you on a small detour, which might seem a bit bizarre, but let me try it out. I did read Max Tegmark's rather good story or pedagogical book, depending on your point of view, called Our Mathematical Universe, in which he goes through quite a lot of the strangeness of quantum mechanics. And he introduces the idea of parallel universes or multiverses, which, if one interprets quantum mechanics very literally, are hard to avoid, quite troubling. And there are various levels of implausibility for the multiverses. When there are multiple universes all the same as ours, but then the next level, the level that does go all the way up to level 4, but level 2 multiverses are parallel universes where the laws of physics are the same, or should I say science. It's just the fundamental constants that are different. And for those who take the view that the fundamental constants have been fixed to be just right for life, that's quite an appealing thought, that we happen to be in the right multiverse. But actually, in the world of materials, we've been generating our own multiverses without calling them that. And what we do when we look at materials for electronic operation as semiconductors is we vary the dielectric constant and we vary the mass. And in that way, we change the constants that determine what sort of physics we see. So you're staring at a very simple example, which is a positive and a negative charge, which is what we have in a hydrogen atom. And if you put those in a vacuum, the Coulomb interaction, of course, sets up the Bohr hydrogen atom with its quantum states. The n equals 1 state is 13.6 electron volts below the vacuum level, is a huge energy. I can go on helium, and there I have enough electrons that I can contemplate spin 0 and spin 1 excited states. And there, because of the different spatial wave functions, I get large energy differences, perhaps 1 electron volt as the spin exchange energy. I could go all the way to the parallel universe of inorganic semiconductors, where I bathe the electrons that are accessible, the filled electrons, the filled valence band states, top of the valence band. I bathe them in a background dielectric constant due to the more tightly bound electrons, which could be pretty large, typically 10. And then if I put a periodic lattice potential in the background, I rearrange the dynamics of electrons and holes, and I reduce their mass, typically to 1/10 of an electron. So what was 13.6 electron volts is reduced in energy, the positive negative charge combination, to the Mott-Vannier exciton, which is a binding energy of perhaps 10 milli-electron volts, 1,000 times smaller. And in that world, for the most part, we turn off the Coulomb interaction. We think of electrons and holes traveling oblivious to the fact they're carrying a charge, because they're pretty well screened. And of course, when we think of a silicon solar cell, we presume that a photon is absorbed and it produces free electrons and free holes, which is true at room temperature. So those are two very different universes where very different things happen because we've got different masses and different dielectric constants. The organics, the molecular semiconductors, sit very uncomfortably in the middle. The relative dielectric constant is not much larger than 1, but it's much smaller than 10, and a reasonable value is 3. The refractive index of most organics is below 2. And the masses are higher. They're typically, for the materials we've been talking about this week, of the order of the free electron mass. So what that does is to put a Coulomb energy that binds electron hole to be quite large, maybe half a volt, much larger than 10 MeV and much smaller than 30.6 electron volts. But it does mean that the excited state of an organic semiconductor is a bound exciton. And by the same token, the exchange energy is large, perhaps half an electron volt. So it's a very broad brush view, but by that very simple measure of those two parameters, mass and dielectric constant, the organics are, by definition, a set of materials where we are constantly needing to worry about the Coulomb interaction. So an indication of that, and obviously I'll come back to this, is the difference between singlets and triplets as we find them in molecular semiconductors. These are some images from a recent paper from Antonis Harvatis and Tomio Montserrat and others, looking at excited states on a pentacene molecule and in a pentacene crystal on the right. And for the singlet excited state, singlets like to delocalize because that reduces the exchange interaction. You can see that the singlet is relatively well spread over adjacent pentacenes. If we switch to the triplet, it is a much more localized entity. You can see that on the right-hand side of the screen, sitting primarily on one pentacene. And that spin triplet state for pentacene is very much lower in energy than the singlet. In fact, it's about half energy. And if it were to emit, that would be, of course, phosphorescence. So that problem of the triplet that lurks around in most of the organics, except those have been specifically designed to avoid it, is something that has had to be engineered in organic LEDs. The singlet excited state, which is produced by photoexcitation or electron hole capture, from which we can get the emission that we get in OLEDs for OLED displays, is there, but there's a lower lying triplet, perhaps half an electron volt lower, and as one does things to bring that to a smaller value. And statistically, 3-to-1 spin statistics would suggest that only 25% of electron hole capture events produce singlets, and that would limit the efficiency of OLED displays. So there's been a huge industry in making use of what would be otherwise wasted triplets. The one that is used in today's displays for the red and the green pixels is to energize or to make possible fast enough phosphorescence from the triplet to the ground state. And that involves putting in strong spin orbit coupling with an organometallic complex, and it's iridium that produces the best results. That hasn't yet been engineered to work for blue. And Troy mentioned this earlier this afternoon, but what is actually employed in today's blue subpixels in smartphone or TV displays, OLED displays, is to make use of triplet-triplet fusion. So the scheme on the left is electrons and holes capture and one another and produce a quarter singlets, 3/4 triplets. The singlets decay promptly, giving prompt electroluminescence, nanosecond lifetimes. The triplets will accumulate, and they actually accumulate to a high enough density that the most likely event that destroys triplets is a fusion. Two triplets fuse to form, and we had Troy talk about it earlier, ideally a singlet. and then that singlet can then produce electroluminescence. Experimentally, it's rather easy to see it. What has been done here is to drive an LED with a square wave pulse, and on the off point, the light doesn't drop straight away. It drops quite slowly. This is measuring it over 10 microseconds. That drop-off can be modeled quite accurately to this bimolecular triplet-triplet fusion reaction, producing quite a lot of the light. Troy mentioned that our paper that we published in 2017, where that reaction can be up to 70% efficient. It's a very different world to inorganic LEDs. Now, I mentioned in the abstract, I've talked about singlets and triplets, that we've been also looking at doublets. So this is a little dive into a topic that came quite unexpectedly to our group, and I'll run you through some results in the last few years to give you a sense of why we're doing it and why I think there are some future opportunities. So the rather complex molecule that has worked very well for us is this thing here. What you see is a carbon which has got 3 bonds to 3 chlorinated phenols, and therefore it has 1 electron, pz electron left over, which is a singly occupied molecular orbital. It's coupled through to a carbazole. That's the red part of the molecule. And rather miraculously, this molecule is very fluorescent. It has a very high luminescence yield. It emits in the near infrared, 700 nanometers. And with it, we were able to make some quite efficient organic LEDs, which we think avoid the challenge of wasted triplets because they're not part of the excitation set of possibilities. What's interesting about these materials, and I'm referring here to work that Tim Heal, who's now at UCL, developed in Cambridge, and he gave a beautiful short talk earlier in the week, is that for symmetry reasons, just the simple radical core, the TTM core, itself not luminescent. The problem is that the mixing of the HOMO to SOMO and SOMO to LUMO causes an allowed transition at a high energy, but a forbidden transition at the lower energy, and that causes that transition to be forbidden. On the other hand, if you stick something else on the end, as we've been doing with these carbazole groups, I should mention that it's Feng Li, who was a visitor with us from Jilin University, who has done a lot of work with these materials. What that does is to change the HOMO, which is now associated with the carbazole rather than the radical center. And that transition between the carbazole HOMO and the singly occupied level on the TTM radical is quite strongly allowed. The absorption strength has come up quite nicely. Clearly we've redshifted. And it's that gives us enough oscillator strength to get these very useful optical properties. We've measured up to 86% luminescence yield, which is actually very surprising for a material so far in the infrared. That's unusual for an organic material. So very, very crudely, on the face of it, naively, this is all rather surprising. What we think is happening with the LED working, I should take the scheme through step by step, is that we start with the fully occupied HOMO level on the carbazole, the singly occupied radical level on the TTM group. We think that devices work well if the first process is injection of an electron, which then sits on fills the SOMO, which is now fully occupied. On the face of it, if we bring a hole in, why we would expect to extract the hole from the highest level, which would be back to the level we started with, like a metal. The SOMO apparently offers the same chemical potential for oxidation and reduction, but it doesn't. and we are able to inject the whole onto the HOMO associated with the carbazole. There are two approaches to thinking about this. The one that we proposed originally was that actually there's resonance, because we actually shuttle holes in a blend of this carbazole small molecule system, CBP, so that there's resonant transfer of holes onto the carbazole on our emitter. So we are able to put the hole onto a deeper level than the most energetic level from which we could have extracted an electron, but it certainly works. The other thinking, which was developed as a very nice paper where a lot of work was done by Jean Predas and his group, is that we have to take into account that when we charge the radical center, we actually change its energy, so that the ground state system, the energy for the SOMO is with a single electron on is actually quite high, sorry, quite deep, quite low lying. It's only when a second electron is placed on it that it ends up at the high energy that we associate, which we associate with the transition back of that electron back to the carbazole group. So this role of charging of the site, which in the physics world would be called the Hubbard charging energy, turns out, well, as it probably should do, to play a large role when we are looking at single and then double occupancies of these states. It's not the usual semiconductor dilute regime. I'm briefly going to mention some stuff we haven't published. It's very much the way Emrys Evans, in a lecture in Swansea. And the thought we had is that there is literature around the place going back quite a long while, as there always is with these systems, that indicates that it is possible to transfer energy between doublets and triplets whilst conserving spin. We start with a ground state spin 1/2 on the doublet molecule. The triplet excitation has spin 1, but 1 minus 1/2 is 1/2. So that can be spin conserving. The systems we've been looking at are LED systems using so-called TADF molecules. These are molecules with donor, and that's the carbazole groups here, and acceptor, which is cyano groups character, where the excited state has a small exchange energy, so there are singlets and triplets nearby, and they've been shown to show fast intersystem crossing and reverse intersystem crossing, and produce very efficient LEDs that avoid wasted triplets. For our purposes, what's attractive about them is that they have singlet and triplet excitations that at similar energies. And we were looking at transfer from excitation of this 4CZ IPN molecule to our redshifted doublet molecule. So here you see emission spectra for the TADF, which is sort of bluish green, and the radical in the near infrared. So the scheme is that we're looking in particular for the transfer of energy from a triplet on the TADF molecule to the doublet. And if you look at the scheme which I'm pointing to in the bottom right, that is indeed a process that can be spin conserving, so there is no restriction on it progressing. So what we have got is this TADF host system, which we can excite either electrically in an LED or optically, where there's rapid interconversion initially to form a high population of triplets, but then the reverse intersystem crossing gives the slow emission that's seen in these systems in LEDs made with them. But both are capable of transferring energy to the doublet system, which we've been looking at. These are some LED performance figures where essentially the red curve gives the best performance, much improved efficiency at higher current densities for some technical reasons which are significant. But this is a diode where we have a mixture of our radical TTM carbazole material with a host of the TADF, and it's given a much improved LED. We can track, I can probably go past that slide, but what we're tracking here are normalized luminescence data versus time, either as the instantaneous emission rate or the integrated luminescence. And what's important in a practical sense is that if I can guide you through some appropriate lines, the red line here is the radical emitter, the TTM3PZ. It has a lifetime of about towards 20 nanoseconds. So that's characteristic of this decay here. The pure TADF material shows a lot of its emission not at within 100 nanoseconds, but within 10 microseconds, because the reverse system crossing required to get singlet emission is very slow. And what we've done by transferring the emission, which is now the redshifted emission, where we initially photo-excited the TADF material, is to massively speed up the emission as we come off the black curve. The useful curve actually is the blue one. We've managed to take away a significant time delay, which is actually a big improvement for those who like to engineer LEDs. So that's the doublet systems. I have to say there are all sorts of other possibilities about where the spin properties play an even more direct role. Now, I'm using a fair bit of time to talk about light emission. I want to turn to issues to do with photovoltaics, partly because it's important and perhaps equally because it's interesting. And of course, photovoltaics are best known in photosynthetic systems, where we have obviously these wonderfully specific and complex structures that involve antennae molecules that absorb light, transfer energy as excitons down to the reaction center, where electron and hole are separated, and the electron off goes to do reductive chemistry, and plants grow. What's interesting in them, looking at it from the sort of electronics perspective, is that there are at least two length scales that are certainly interesting and surprising. And the first is that there is efficient exciton energy transfer, a topic much investigated under the general heading of quantum biology as to how that can happen coherently. But the separate issue of how it is possible to separate charges beyond their recombination range must also involve relatively long length scales. So as soon as we're looking at getting charge separation, the big question that must always be there is, how is it possible for electrons and holes to separate far enough that their Coulomb interaction doesn't hold them back together? On the first topic of energy transfer, David Beljean gave a beautiful talk earlier in the week and referred to some Cambridge work on very well organized nanofibers made with conjugated polymer segments. These are materials that Ian Manners, then in Bristol, now in British Columbia, had devised. And I want to briefly mention some work that we were doing a couple of years ago. In Cambridge, it was Michael Price who did the optical measurements. But these are structures where it's possible to assemble fibers of up to a micron in length, where the core is extremely well crystallized conjugated polymer. Back then, we were working with a polyfluorine oligomer, typically a 14-mer. David was mentioning work with polythiophene, which is more recent. It's possible to grow these in a sort of living growth way. So you can grow the core and then in solution add ends that are different. And the difference here was to stick some polythiophene on to the ends on the sort of flexible corona that obviously helps stabilize the material in solution. But what that sets up is a system where we've got a blue core with and a red corona at the two ends, so we can track, if we photo excite in the blue, we can track how far and how fast energy transfers to the red polythiophene ends of the structure. And the remarkable thing is that, the remarkable discovery is that we have measured exciton diffusion ranges up to 340 nanometers, which is a huge distance. It's an order of magnitude more than nature chooses to use in photosynthesis, and similarly a very much larger number than is ordinarily found in the organic systems that we usually investigate. I'll just briefly show you this beautiful confocal fluorescence image from Bristol showing these structures more than a micron in length, and you can see the blue luminescence from the core and the orange from the thiophenes. And what we've been tracking obviously is the speed with which energy transfers from blue to orange. And it's distance depends as well, from which we extract this huge diffusion range. David presented some really interesting ideas about schemes which enable the excitons to delocalize along the stack associated with vibrational excitation. But it's really surprising and potentially very important, because we've now got materials that are where the diffusion range is larger than the thickness of material needed to absorb light. So if we can think of these as potential, if you like, perfect antennae for funneling radiation absorbed to a surface, maybe to a detector or new solar cell designs. So to the solar cell world, where the practical systems we have been working with for 25 years or more do not have this large exciton diffusion range. We rather cheerfully mix together electron donors and electron acceptors to form a bicontinuous network, if we're lucky, of donor and acceptor, and then we put electrodes to either side. And the design principle is that electron hole pairs can be generated by photo-induced electron transfer if the exciton is at or close to the interface between donor and acceptor. And we arrange that that's the case by this nano-structure with length scales that are smaller than the exciton diffusion range. My slide is out of date, it should say 18% there, but these very, very crude approaches, and there are many, many of them. I would include the dye-sensitized solar cell from Michael Gratzel in that broad category, but also these days it's very much the organic donor-acceptor mixtures. They can work very well. The scheme which I've just described is one of electron transfer. We photo excite, in this case it's a polythiophene, and then there's an electron transfer from the polythiophene to a lower lying unoccupied level here on a fullerene. And this particular system of polythiophene versus fullerene provided an absolute mainstay for the field until not many years ago. And from nowhere, we now have new material systems that have raised efficiencies for organic solar cells. They're now at 18% against the solar spectrum, which is a remarkably high number, probably a useful number. One of the surprises, which I'm not going to talk about this afternoon, is that the cartoon that you can see in front of you appears to throw energy away as we take an electron off a conduction band state on the thiophene and dump it onto a lower lying energy on the fullerene, and that is indeed the case. So for that particular system, it takes a 2 eV photon to produce about 0.8 volts open circuit voltage. But in new designs, these so-called band edge offsets have been reduced to close to 0, and it is still possible to get efficient long-range charge separation. It is, to my mind, that is still quite mysterious. So to come to some, we've been looking at some of these new very high efficiency systems. One that is enormously important, isn't the current record holder, is what's called in the trade PM6Y6, which are acronyms for these for the donor polymer and the molecular acceptor. And Y6 seems to be rather miraculous. It has plenty of electron accepting components, the cyanide groups. It also has electron donor groups, these fused thiophene rings here. And that push-pull character seems to have some quite magic properties, but it's an absorber well into the infrared and produces these rather efficient solar cells. So in Cambridge, my student, our postdoc, Alex Gillett, was interested in actually an old story, and that is that, I need to take you briefly through this cartoon. When we, if a solar cell is working like a textbook solar cell, it's not very different to a light emitting diode. FC stands for free charges. We should have electrons and holes which are diffusing in the device. They will collide with one another. If it were an LED, we would be pleased to see that form an exciton, which would then produce light emission. In a solar cell, that is a natural process of recombination and re-emission, ideally. That should be an inevitable process in a well-working solar cell. The here is the concern here is that recombination of the free charges is quite likely to form exactly the same singlet-triplet ratio as is found in organic LEDs. There's no reason why it shouldn't. And the particular concern is that these singlets and triplets will be, if you like, charge transfer states with the electron and hole on the different materials. But if in the triplet manifold, there is no reason why we can't do a back charge transfer down to the lower lying triplet, which will be sitting in our case, the lowest triplet will be on the non-phosphorescent acceptor. And that is a worryingly effective pathway for non-radiative recombination, which will be manifest primarily as a voltage loss in a solar cell. And it is indeed voltage loss that is what limits the performance of organic solar cells. There are only a few groups that go looking for them, but whenever they do, we usually find them. This briefly is some stuff we published in 2016. It was the work in Cambridge of Matt Menker. We're working with materials from Guy Bazin and Gwyn Nagayan in Santa Barbara. But it's a fullerene system against a rather good donor with the acronym PIPCP. And what we can see actually from transient optical spectroscopy, where we can pick out triplets from their excited state absorptions and also charges from their polaron absorptions, is that the polaron concentration, the charge concentration here of holes, falls with time. This is 100 picoseconds, this is a nanosecond. But at the same time, what is building in instead are triplets. And that happens more or less quantitatively. So if we take the lowest fluence data, these orange data points, the whole concentration is constant to 100 picoseconds and then starts to fall as we see a rise in the triplet population. Now that, we said very confidently, was the reason why we could get a good quantum yield at short circuit when recombination is discouraged against charge collection. It doesn't produce a high open circuit voltage, and it isn't a very good solar cell. So Alex has been looking at some of these, or many of these new non-fluorine acceptor systems, and here are some complicated spectra, which I'm not going to take you through, on PM6Y6, which is a sort of canonical, excellent 16% efficiency solar cell. And in transient optical transmission, what you see are increased transmission where we've bleached the ground state here for the PM6 donor, here for the Y6 acceptor, and then the features below the line are absorptions due to the presence of excited states with redshifted absorptions, and in addition there's some electroabsorption. But lurking quite a long way in the infrared is a feature which we can demonstrate in various ways is clearly associated with a triplet on the Y6 acceptor. The time at which that triplet emerges depends on the amount of the initial photoexcitation density, because there's the process of recombination, bimolecular recombination is bimolecular, so it goes faster at the higher fluences, as you see here. Alex worked out that actually, in spite of this being a very good solar cell, relatively speaking, it still shows quantitative triplet formation, and at open circuit, 90% of the excitations decay via the triplet channel. So Alex has looked at a great number of these systems, and here are some of them. He's also set up a collaboration with the Oxford group, it's particularly Alberto Privatera, working in the Bill Myers Center for Advanced ESR, and has been looking for photoexcited EPR, which is associated with triplets, as well as generated by intersystem crossing and by recombination. What the ESR can do is pick out it's not sensitive to recombination, bimolecular recombination, but it is sensitive to geminate intersystem crossing. And it turns out that for the fullerene systems, which somehow are yesterday's acceptors, quite generally there is geminate triplet formation, which is quite surprising, and quite a concern. If we go to the non-fluorine acceptors, we just don't see geminate triplet formation. But for most of them, we do see non-geminate, and that's picked up from Alex's transient optical absorption measurements. And again, I mentioned that for this excellent system, PM6Y6, that proceeds qualitatively. So there are some systems where we don't see geminate triplets at all. These systems where the acceptor is IEICO 0F and 2F, they're materials again from Santa Barbara. And it's very interesting. They're not the most efficient systems for other reasons. They're about 12% power conversion efficiency, but they are. But David Beljean and his group have done some beautiful calculations. And what turns out to be a really interesting parameter that has not been so seriously considered until recently is that the strength of the overlap between donor and acceptor can switch on enough hybridization to invert the energy ordering of the charge transfer states at the interface, pushing the singlet below the triplet. Essentially, if the well-separated triplet hybridizes with the lower-lying localized triplet here on the acceptor, that can work repulsively, and it is the singlet that can drop to a lower energy. So that's the thinking that we're developing at the moment, we think there is sort of life in new designs to control what goes on in photovoltaics, where it may not be the parameter that has been of greatest concern, but the possibility of non-radiative decay via the triplet channel is there, and it needs to be engineered out. on that point, I'm going to stop. I have enough slides to go on quite a lot longer, but that's where I expected to get to, and I will stop there. Thank you all very much.
Thank you very much, Sarah, for this wonderful tour de force. And I'm sure that you will be happy to take a few questions. I'm just taking a look at the chat, where I actually do not see any questions yet. So maybe let me start. So for these different spin species, especially the doublet species, I mean, what is kind of your kind of wish list for spectroscopic techniques? I mean, it's like a combination of EPR together with spectroscopic kind of optically resolved techniques would be the way to go. So what is sort of the best possible spectroscopic setup that you're thinking of, like together with theory support, of course?
It's a
theory question.
That question rather floors me. I think one of the questions that is rather intriguing is what sort of engineering can we do with the radical, with the SOMO orbital? To what extent? I mean, does it need to be very localized around a single carbon, as in the example that I've shown? Or is the scope to couple it perhaps in an excited state, if that orbital were associated with having an electron present on it, might we be able to delocalize? Because one of the things that one can sort of easily say but have difficulty in delivering is that the perfect solar cell made with an organic should not have a non-radiative excited state as its lowest excited state. Okay. And for the doublet systems, the doublet is the lowest excited state and it's radiatively accessible. The trouble at the moment is that these doublet excitations are rather localized and we don't know how to separate them easily. But maybe we could make a fantastic solar cell if we could engineer the wave functions to be more accessible, more delocalized.
Yeah, absolutely.
So I could throw that out as a theory question. I think I've deflected your question. I don't want to.
Yes, absolutely. And of course, from our side, like from the theory side, I mean, we're trying to work a lot with spectroscopy too. And one of the basic issues always concerns like delocalization or localization of excitations, and I think that's it's a key issue.
Right.
So I'm taking another look at the chat here. I do not see any questions, but Jochen, is my chat up to date? I'm not sure whether I've done anything to my display here. Oh, yes, I mean, now I actually see it. So question from Matthew Hutton. So thank you, Sarah, for a very clear and interesting talk. Do you even encounter a strong electron correlation within these molecules? And if so, what effect does this have on the reliability of a single particle picture used to understand the electronic transitions?
Well, I think any correlation must be, any description of excited state, molecular excited states, if we use single particle models where these are mere approximations. To some extent, the story I was mentioning that we now have to think about the charging energy. I think that is a correlation, isn't it, by my book? But I hope I'm not missing the point. But I think it is. We are constantly using models that are borrowed from perhaps conventional semiconductor worlds. Because the single particle descriptions are easy to contemplate, and when they work and when they don't is always the issue.
Here's another question from Tracy Clark. Thanks, Richard. What is inducing the flip and the 1CT and 3CT energies?
The argument is that it is if there is sufficient overlap of molecular orbitals between donor and acceptor, it is hybridization involving localized levels on one side of the heterojunction or the other, that produces a sort of CT state that has got had its energy rearranged through how it is hybridized with the localized excited state.
Thank you. Another question from Curiel. Is there a fundamental physical difference between Dexter and Foerster transitions?
Well, there is. The way it's generally, the way we think of it, the Foerster is a sort of virtual photon transfer and can be quite long range. There's an oscillating dipole associated with the optical transition on the donor, which is sort of received by the acceptor. The Dexter transfer is much more like direct electron tunneling. Technically, it is a two electron transfer and is much shorter range. We were hearing about it from Troy earlier as the process that must be in play, looking at triplet transfer between organics and inorganic nanocrystals.
Second remark, but by second quantization, it looks similar.
Okay.
Maybe this is getting into a longer discussion.
I've said what I've produced the sort of the textbook view, but Foerster transfer is well parameterized in the simple way I've described it. Again, David Beljean explained that one has to do more careful things when the states that are involved, the initial and final states, are themselves more delocalized, that the point dipole approximation that is generally used starts to fail. But Foerster transfer can operate over far greater lengths over which there can be direct electron tunneling.
Thank you very much.